Welcome. You have no idea how bright the lights are up here. I can't see anything. But I want to get started on the Emiliani lecture because we have a very tight time window. And I just wanted to start off by introducing myself. I'm Peter Swart, who's the incoming president of the Paleoceanography and Paleoclimate Focus Group. And the Emiliani lecture is actually co-sponsored by our focus group and the Ocean Sciences section. And our speaker this year is Richard Zeeby, and you can see his title up there and his picture. But before I turn it over to Richard, I just wanted to give everybody a little bit of a taste of Cesare Emiliani and refresh you as to some of his accomplishments. Of course, Cesare died in 1995, and here he is at the mid-year meeting of the AGU in Baltimore in 1994 with his friend and nemesis, Cesare Emiliani. He was a member of the University of Miami faculty for 40 years, and I actually had the good fortune to overlap with him for about 12 of those years. He was the chair there most of the time. He's considered to be the father of modern paleoceanography, and he had several awards through his life. His most famous contribution appeared in 1955, and this is a scan of the actual reprint. And in there, he was one of the first person to actually measure the oxygen isotope composition of the oceans using foraminifera. Here he has his temperature scale. He interpreted this as temperature, but you can see clearly the modern and the last glacier, 5E, as he called it, and the temperature ranges, which later Nick Shackleton interpreted, changed the interpretation to include a large portion of ice volume. So I just wanted to tell you a little brief story. I have many, many stories. I could tell you sit here the whole day and tell you Cesare Emiliani stories, but this is one which is sort of interesting. Some years ago, I got his machine from his old original machine, and I was looking to make it into an exhibit, and I got some information from Bob Clayton, Chicago, and this is Harold Urey sitting at that same desk that we had a picture of Cesare earlier. Here's Tosh Maeda, Harmon Craig, and Cesare walking down a street in Chicago. And in 1953, Sam Epstein and Tosh Maeda published the first paper on oxygen isotope compositions in the oceans. So this was published in February of 1953. And Bob Clayton sent me a letter that Cesare wrote to Tosh Maeda when he was traveling to Paris on a French ocean liner. And I'll just go over this, enlarge it a little bit. And it describes the first attempt to collect oceanographic samples or samples from ocean water for isotope analysis. So he starts off that he very distinguished crossing of the Atlantic with 2 days of tempest but no seasickness. I lowered my pail with the astonished admiration of the passengers and crew a few hours after sailing. The pail was immediately up and I was down at the same speed, and the pail, in fact, kept flying across the water, occasionally hitting the surface and bouncing upwards. I did not succeed in collecting more than a few cc's of water. To the people nearby, I explained I was experimenting with a new type of container with an opening that, when in very rough seas, would not be filled with water. Everybody expressed admiration with the brilliant results of these tests. Secretly, however, I was ruminating. This is actually, I think, a cross between ruminating and imagining, to find a system to fill up the damn pail. I quickly discarded such cheap devices as drilling another hole in the bottom or collecting samples from the swimming pool. Fortunately, while I was busy with these thoughts, the boat's engine collapsed and the boat stopped. I dashed out and collected a nice sample of water. And then the next letter goes on. It's full of quite funny things, but then I'll just skip to the end. He says, after this, I went to the captain. It was a French boat, remember. He says, Mon capitaine, I told him, do you have a faucet straightly and shortly connected to the sea from which I could collect samples of water for oxygen isotope analysis? Mais oui, he answered. We indeed have a faucet at 7 meters of depth below the sea level. Just give the bottles to my chief mechanician, he says, and he will fill these up at the proper intervals and write out the labels with the geographic positions and the temperature of the water. We have a thermometer right there. Merci beaucoup, I said. And the following painting shows how I collected the samples. So here's his little sketch here. And there's the faucet. And then when we reached Le Havre, I had the bottles filled up. I put them in a case, screwed it up, and carried to the company back to New York. By this time, they are back at the French Line Pier 88 in New York. The company cannot send the case to Chicago, therefore you have to find a shipping agent, and so on. And then he finishes at the bottom of the letter, I hope to find a letter from you here in Paris. I ran all the way from Chicago to get it, but alas, no letter was here. Too bad. Greetings to everybody, namely Rosita, who was his wife, and myself. So, that's just a little bit of insight into Cesare's wit. Perhaps the best example is when NSF sent him his own proposal to review. And he, needless to say, gave it a very good review. You can find that in the Journal of Irreproducible Results if you want to look at that. I recommend it. It's quite funny. And so Richard Zeeby is our 12th, I think, Emiliani lecturer. The first one was Nick Shackleton back in 1999. And Richard has his master's degree from Bremen, a PhD, also from Bremen, and I didn't put any more dates here, just so you'd have to do the mathematics yourself. But he's currently a professor at the University of Hawaii. And one thing which I recommend heartily to all people who study carbonates and isotopes in seawater is this book, which he said he had made the mistake, or actually the fortune, to write. It's still a very good seller on the Elsevier stand, but it basically explains a lot of particularly stable isotope and boron isotope chemistry in seawater. So with that, I would like to introduce Peter Schlosser, who's the president of Ocean Sciences Section, to present Richard with not a check, but just a certificate.
So on behalf of the paleo oceanography and paleoclimatology focus group and the ocean sciences section, I would like to present to Richard a certificate of recognition for being elected Emiliani lecturer in the year 2012. Congratulations, Richard.
Thanks a lot.
And if you see Richard's eyes wander seemingly aimlessly, it is because he's really blinded by two bright lights up here. So don't worry about that.
All right, thanks a lot, Peter and Peter. I got to say, I'm truly honored to give this lecture, and I also want to thank the committee for selecting me. And the first thing when I got this invitation was to think, wow, me, interesting. And one reason to find this a little strange is because I'm maybe not. If you look at the list of the previous speakers in this lecture, I'm maybe not your typical paleoceanographer. My background is physics. And I do a lot of theoretical work, and I'm going to show some of this. But I also think this lecture should not be all about me. I think it should be about the contributions of the field, and it should be about science. So I got to give you a warning. There will be some serious scientific content. And it should be about people like Emiliani, for example, who were giants in our field. And it should also be for people who are not in our field to show them what we're actually doing. And so I'm going to stay away from, I'm going to refrain from making long thank you speeches. There will be acknowledgements throughout the talk, and at the end there will be lots of credits. And so this is definitely a special occasion for me, and so I prepared something special, and I made up a little story for you. Here we go. 500,000 years from now, year 502,012. As the Onyx spacecraft approaches planet TR23A, the civilization on the planet has long ceased to exist. Captain Emilio Cesare assembles a team to take ice and sediment cores from the planet's surface to investigate its climate history and the demise of the civilization. His initial results show the onset of a dramatic climate perturbation about 500,000 years ago, which Captain Cesare will later call the Holocene-Anthropocene boundary. Cesare presents his initial results from ice cores. And what they find is that there were like 500,000 to about 1 million years before their time. There were periodic variations in the atmospheric CO2 concentration, and they're going to have a hard time figuring out what the cause of this variation was. And they also find a dramatic rapid increase about 500,000 years before their time, which they then call, or will call, the Holocene-Anthropocene boundary. Cesare also presents results from sediment cores, and what they found in sediment cores was that at the time of the boundary, there was a dramatic change from carbonate to clay in the deep sea sediments, which indicates that there was dramatic ocean acidification at the same time when they saw an increase in the carbon dioxide concentration in the atmosphere. Encouraged by his groundbreaking initial results, Captain Cesare is eager to continue his studies. However, the Oceanic Science Foundation cut his ship time and funding due to a shift in priorities. It will take Cesare Oceanic decades to return to his project on planet TR23A. And now I owe you a couple of references, which will all be published in 500,000 years from now. And also in quite strange journals. And so we will get back to Emiliani at the end of the lecture. No, to Emilio. And so the first title of my talk is No Future Without a Past. And this is a question mark, and you can sort of interpret this or ask this question in various ways. You can ask, for example, do we have a future if we ignore the past? Or you can ask the question, are we confidently able to predict the future if we ignore the climatic history of the planet? And we will get back to this throughout the talk. And now for something completely different, Cesare Emiliani and Harold Urey. So you may have seen this picture a few times, but I really like it because you can see Urey and Emiliani. This is in Chicago in his lab, both together. And if you consider Emiliani the founder or the founder of paleoceanography, you probably want to consider Urey the godfather of paleoceanography. And I got to admit, I'm fascinated with this guy here. He got his Nobel Prize in Chemistry in 1934 for the discovery of deuterium, and he went on to study stable isotope systems. He went on to study the planets and the moon. And one of the groundbreaking papers that everybody should read when you're studying isotopes is this one here that was published in 1947. It's the thermodynamic properties of isotopic substances. And in this paper, he lays essentially the physical basis for isotope fractionation in thermodynamic equilibrium, and this is the basis for essentially most of the isotope work that we are currently doing or doing today. You got to point out that he was not the only one working on this. There's an interesting paper by Waldman, published in 1943, which has very similar equations. At the same time, Biegeleisen and Meyer published a paper in which they also pointed out the usefulness of stable isotopes, and they also provided the equations to calculate fractionation factors. But Urey, I think Urey was one of the guys who really understood the far-reaching implications of these of the theory. And the rumors are that he imagined after he gave a talk somewhere else that he may have a paleotemperature using isotopes, and he wanted to find out whether the dinosaurs, or why the dinosaurs had disappeared, and whether this was caused by a dramatic climatic shift. Also, these calculations of these fractionation factors, that's not something that has been done 60 years ago and it's not out of date. I just gave a talk yesterday in a session about sulfur, and you can calculate fractionation factors between water and sulfate ion, for example, exactly based on the theory that Urey has proposed in 1947. Nowadays, we make it a bit more complicated to calculate the molecular oscillations, but the theory is essentially the same as proposed by Urey. And so enough about Urey. Let's talk about Emiliani. So Emiliani was less of a theoretician as Urey, for example. So Emiliani was probably more a man of action. And he applied then the paleothermometer to deep sea sediments and actually came up with tertiary bottom water temperatures, which in some sense still hold up today. And one of the big contributions was that he looked at Pleistocene temperatures, and he found 7 glacial cycles from a Caribbean sediment cores. And I'm going to talk about this in just a second. So if you want to summarize his contribution in just one sentence, Bill Hay wrote this in 1999. His discovery revolutionized ideas about the history of the ocean and of the glaciations. But as Peter has pointed out, he also had a good sense of humor. And Jim Zakos, before the talk, he sent me a review that Emiliani wrote in 1994. It was published in GCA, and he wrote a book review of Annual Review of Earth and Planetary Sciences. And he went through all the different chapters in that book And he also commented on the chapter of marine black shales by Mike Arthur and Bradley Sageman. And he said, this is an excellent chapter on black shales if that is what grabs you. Personally, I think the black shales stink, especially when they're fresh. And so Emiliani also has a species named after him, Emiliani huxleyi. I personally think it should be a forram, but he does have a species named after him. And so Emiliani was a broad talent. I mean, he did not only look at Pleistocene temperatures, he also published a paper in '69 on underground nuclear explosion and the control on earthquakes in science, and he also published in the Journal of Theoretical Biology. So one of the things that I think is important to realize is that, you know, given this contribution of these people, we are standing on the shoulders of giants. And this was already recognized by Newton, who said, if I've seen further, it is by standing on the shoulders of giants. And it appears sometimes that we tend to forget what are the big contributions that nowadays we take for granted. And one of the big contributions of Emiliani clearly was that he revolutionized our thinking about the ice ages. And if you, this is Emiliani in Yuri's lab. This is here in the Northern Hemisphere glaciation during ice ages, and this is Milankovitch. And at this time, when Yuri did his work, Milankovitch was not at all accepted. Nowadays, it's one of the important cornerstones of paleoceanography, but this was not the case at the time. And the prevailing view was that there were 4 glacial cycles during the Pleistocene ages and not more. And this here is a quote from a textbook by Richard Flint, who was at Yale in '47. He writes, the 9 heat minima deduced from the Milankovitch curve do not agree with the geologic evidence, which, though admittedly fragmentary, records a maximum of only 4 glacial cycles. And this was a prevailing view at the time, and this goes on. This goes back to Penke Bruckner in the beginning of the century, and these ideas about 4 glacial cycles went on to be in textbooks until the 1950s and 1960s. And one of Emiliani's really great contribution is that he showed that there were a lot more glacial cycles throughout the Pleistocene, and based on this Caribbean core A172.6, he picked out at least 7 glacial cycles. And nowadays, this is common knowledge. This has been transferred way out of our field and is being recognized. So here comes something which I call the triple choice segment, and I'm going to talk a little bit about basics of forams and isotopes. And if you're not in our field, you may not have any idea what I'm talking about, so I'm going to explain this. And if you know the stuff, you have other choices. So if you don't know, you can watch. If you know this stuff, you can sleep or you can think, or you can do something completely different. But if you want to think, try to figure out what is the square root of 1764. Okay, so this here is a foram. This is Orbelian Universa. And the scale we're looking at is about 1 millimeter. So this here is the calcite shell. And here we have another species, that's Beloides. And when these guys die and they produce these calcium carbonate shells, they sink to the sediments, and you can take then samples from sediment cores and measure, for example, stable oxygen isotopes in these forams. And that's essentially what Yuri proposed and what Emiliani carried out. And so what we're interested in, what the paleo temperature or thermometer is the isotopic fractionation of, for example, O18 and O16 between the water and the calcium carbonate, and this factor we call alpha. So you can think of it in a very simple way as an isotopic exchange reaction where you have an oxygen and 16 oxygen and an 18O in water, and you just flip these between the two compounds. So exchange the 18O in the water with the 16O in carbonate, and you get something like this. And the question is, what is the equilibrium constant of this reaction? Essentially, what is the isotopic fractionation factor? So how is the partitioning of distributions of isotopes between the water and the calcium carbonate? And so what we use to express this is the fractionation factor, which is defined as a ratio of O18 to O16 in carbonate versus the same ratio in water. And these numbers are usually close to 1, so instead of writing alpha being 1.030, we just say calcium carbonate is enriched or isotopically heavier by about 30 per mil. And so what is being done to measure this is you take the isotope ratio of your sample and the same thing of a standard, and again you just express it in per mil by taking away 1 and taking times 1,000. And then once you have measured your two values, for example the delta of the water and the delta of the calcium carbonate, you can determine the fractionation factor. And this fractionation factor depends, for example, on temperature. So Emiliani knew this, and he also knew that it depends on the O18 of seawater, and that was the basic idea of looking at these Caribbean cores to find out what was the temperature and ice age variation throughout the Pleistocene. So there are a couple of things which influence this fractionation factor. There's temperature, O18 of seawater, which is a function of ice volume. The more ice you build up on the continents, the heavier, the more enriched the water will get. And there are other effects, and one effect here is seawater chemistry, which pointed out by Howie Spiro and others in 1997. And here's actually where I came into the game, because Jelle Beimer and Tito Vglado at the AVI, they engaged me to find out or find an explanation why seawater chemistry, for example, affects carbon and oxygen isotopes in forams. So this was just for those who have no experience in this field, and the square root of 1 is 42. Okay, so coming back to Emiliani and scientific achievements. So if the technique that he used, and he was aware that these oxygen isotopes in the foraminifera in the core that he took were affected by temperature and by salinity, it was clear that there were a large number of glacial cycles throughout the Pleistocene. And this is one contribution, of course, that is relevant to other disciplines, and there's a lot more, and this list is, of course, incomplete. I'm pointing this out. But there are a number of things that paleoceanography has contributed and which has gone way beyond our boundaries, and I'm going to focus on a few things. So I mentioned ice ages. For example, there's a massive rapid carbon release, which probably 30 years ago nobody would think about that this is possible. And I'm going to talk about a few other things, but also in terms of physical oceanography, major rapid changes in ocean circulation which have been documented using deep sea cores is something that people pay attention to. And so, no, I'm a theoretician, so I usually don't go on drill ships and sail the ocean. So some of my friends are making fun of me that I'm not going on boats, but here's proof. So I was in Amsterdam, and we had a great afternoon around the Grachten, and so I got to thank Frank Peters and Gerald for giving me that photo. So that's the proof. Okay. So for the next couple of minutes, I'm going to talk about massive and rapid carbon release. And the paper I want to start with is this one here by Kenan Start. And this is, the title is Abrupt Deep Sea Warming, Paleoceanographic Changes and Benthic Extinctions at the End of the Paleocene. And there was a recent article in the National Geographic, which I'm going to mention in a few minutes. And I also want to point out that, so although Kenan Start in 1991 were essentially the first to point this out, that there is a major change in the isotope composition, for example, it was known that at the end of the Paleocene there were dramatic changes in the deep sea, and Alan Thomas and others had pointed out before that there were major benthic extinctions at this period of time. And in the same core that Kenan Start used in 1991, they found also that this is associated with a major benthic extinction in this core ODP 690. Okay, so here's some of the data. And on the left-hand side, you have the oxygen isotopes, and on the right-hand side, you have carbon isotopes. And these guys here, these are different foraminiferous species. And what you can see, so even without, in paleoceanography, we like to do wiggle matching, right? So we always line things up and put bars where you're supposed to see something. But even without this bar, you would recognize that there is a large shift, a step function here in the oxygen isotopes, and there is a big step function here in the carbon isotopes. And so this is depth scale. This is the depth of the core. This is 690b. And put some ages up here, but geologists like to change these ages all the time, so I just said it was about 56 million years ago. You can make this more precise, but it's irrelevant for the argument. And here, this time scale, this axis here represents approximately 200,000 years. So this is the important things to remember. This happened about 56 million years ago, and the recovery time here, or the time scale of this excursion, is in the order of 200,000 years. And so to remember, this I'm going to focus a little bit in the next couple of slides, is that there is clearly a large isotope excursion. This has been documented in terrestrial records all over the deep sea records. And this excursion may be in the order of 3 per mil or maybe a bit more. And what Kenan Start said in 1991 was that The slightly delayed shift during the excursion to highly negative delta C13 values in Antarctic surface waters is difficult to explain. And then they go on to speculate about organic carbon and plate tectonics, but essentially at this time it was not clear what may have caused this carbon isotope excursion. And today, so that's one of the achievements that we essentially take for granted, the PTM is known as the best paleo analog for massive carbon input. And there were several articles featuring the PTM, for example, in the LA Times, in the New Yorker, in the National Geographic. And National Geographic has, of course, beautiful pictures. So here you can see Jim Zakos holding up a replica of, I think this is a Welvis-rich core, where you see the transition from the Paleocene to the Eocene. And so this is essentially how Jim appears today. But during his time when he did his early studies on the subject, he probably looked a bit more like this. And here's one of his early papers on the trends in climates during the Paleogene. And so I'm mentioning Jim here, and I also want to mention Jared Dickens, because both of them had an important influence on the way I work on the PTM, or how I think about the PTM. And one of the important, so 1991, Kenan Start published this paper, and they found the dramatic isotope excursion. So in 1995, Jerry and others published this paper, and the title is Dissociation of Oceanic Methane Hydrate as a Cause of the Carbon Isotope Excursion at the End of the Paleocene. And what I want to point this out, that in the title already, it says clearly that as a cause for the carbon isotopes excursion. And in the last number of years, I think various people have misinterpreted or misunderstood that this was a hypothesis for the dissociation of methane hydrates as a cause for the carbon isotope excursion. This does not mean that this is the initial trigger or that this caused the entire PETM. Obviously, to dissociate methane hydrates in the deep sea, you probably need an initial trigger that warms up initially the deep sea or the deep waters, and then you can trigger hydrate release. So that's an important point. Okay, and so for those who have not studied the Paleocene-Eocene thermal maximum yet, here's again a picture of this core that you saw before. This is ODP 1262. And here is the transition from the Paleocene to the Eocene. So you have carbonate-rich sediments before, and then you go to almost entirely clay, which is a clear demonstration of ocean acidification that started from the bottom up. And you can see this on depth transects, how the deep sea got more and more acidic and then dissolved the carbonates, and you essentially, in the deep sea, you're left with this red clay. So we have, during the Paleocene-Eocene thermal maximum, is now probably the best analog for massive carbon release. We know that we have measured this in various records. It's about an isotope excursion of about 3 per mil. Surface temperatures rose by 5 to 8 degrees, and I'm going to say a few words about how fast this may have went into the system. But what's very important is that even if you take different age models, it appears that the duration of the warming during the PTM was probably longer than 50,000 years, and we're having a hard time understanding this at the moment. What you can also see, and I pointed this out before, there was a clearly deep sea dissolution. So the massive carbon input that was associated with the isotope excursion also caused carbonate dissolution, and very dramatic in the deep Atlantic, where the CCD showed probably by in the order of 2 kilometers. And there were max extinctions in deep sea sediments. So benthic foraminifera, as I pointed out before, and this was known before we got isotopes, essentially had the biggest extinction maybe over the last 60 million years. So the question is if what we're doing, we're looking at these events because particularly I'm interested in if they can tell us anything about the future. So what we're doing at the moment is we're putting CO2 in the atmosphere, and we're doing this very rapidly. And so the question is, do we have any paleo analogs? Okay, I have to point this out because there cannot be a perfect paleo analog because humans have never been on this planet. Anybody else has burned carbon in the rate and order of magnitude as we're doing it now. But you will probably find very useful case studies in the past, like the PTM, that may tell you something or give you a scale of how this compares of human anthropogenic input of CO2 relative to the response of the Earth system in the past. And so what you can do is you can try to compare rates. So this here is a plot. This is depth, and these are various foraminifera This year's the delta C13, so the carbon isotope ratio in forams. And all of these, they show a step function. This is from Bass River. And if you take, this here is essentially the Paleocene-Eocene boundary. And in this record, it looks that like the input was on geologic time extremely rapid. And if you take the estimates of, for example, that are out there in terms of how much carbon went to the system and over what time scale, you get numbers like, for example, 2,000 petagrams of carbon over 2,000 years, or maybe 5,000 petagrams over 10,000 years. And the order of magnitude that you get from these rates is in the order of 1 petagram carbon per year. So we can now compare this to the Anthropocene and the carbon input rate that humans are causing by burning fossil fuels. And this here is from Marlin et al. 2007. This is broken down in different fossil fuels that we're burning. This here is the total. And if you take if you take these rates, an average, for example, over the last 50 years, you get something like 4.8 petagrams carbon per year. And if you take the rate in 2010, you get about 9 petagrams carbon per year. What you get from this is that it is most likely that we are doing it faster than the PTM. But in terms of a geologic record, this is an extremely rare event because the order of magnitude of the rate of the carbon input may be comparable to what we are currently doing. And so we modeled this event. And so what we did is essentially we added 3,000 petagrams of carbon. This year is time zero, so this year is the Paleocene-Eocene boundary. We added 3,000 petagrams and in the first initial pulse. And then we added another about 1,500 petagrams with an isotopic composition of about -50 per mil. And in a model, you can do this, and then you can ask the question, what happens to the carbon isotopes, what happened to the dissolution, and what happens to the atmospheric CO2 concentration. And the first thing I want to point out is these are data records. So this is carbon isotope excursion at the Paleocene as measured in deep sea records. And what you see is that this is the initial excursion in the order of 3 per mil, and then they stay there for a very long time. And if you want to sort of replicate this in a model, you need this additional carbon input. If you were just to add the initial pulse, your carbon isotopes would essentially drop back down way too fast. And so we're just hypothesizing that there may have been additional carbon output, or another mechanism must have caused the long duration. So we now believe, even based on different age models, may exceed 50,000 years. Okay, I want to point out another thing. So essentially these numbers are constrained by carbon cycle modeling and by looking at deep sea dissolution, for example. And what you get from then you can determine the isotopic composition of your carbon input or the source. In this case, it turns out to be consistent if you want to replicate this with an input of about -50 per mil in terms of carbon isotopes. So you have another triple choice segment. If you're familiar with the PTM and carbon isotope mass balances, you can go sleep. If you want to think, what is the square of 6.4807? Okay, so I just mentioned carbon isotope mass balance. So the idea here is we have an ocean, atmosphere, biosphere system before the Paleocene-Eocene boundary. And at the boundary, we pump in carbon with a certain isotopic composition, and we want to know what is the size of the magnitude of the carbon isotope excursion. And so your initial mass here, this is the initial mass of your surface carbon cycle. This here is the initial ratio, carbon isotope ratio of your surface carbon cycle. And this here is the isotopic ratio of your source carbon, and this is the mass of the source carbon. And so if you take the products of these two and you add them up, you must get the final isotope ratio times the final mass of the carbon that's in the system. It's essentially a trivial equation. And if you then put in some values, for example, let's assume, just for the sake of the argument, that we have an initial mass of carbon in the system of 36,000 petagrams of carbon, and with initial isotope composition of 1 per mil, and we add 3,000 petagrams of carbon with a source isotopic composition of -50 per mil, then what you get is a carbon isotope excursion in your final composition of about -2.9 per mil. So this is about 3 per mil. This would essentially satisfy the data if you assume that your total isotope excursion was in the order of 3 per mil. But what was also obvious is that this is not the only choice. You can play with these values. You can take less carbon you put in with a heavy isotopic composition. And if you play this game, then you can make a plot something like this here. We have the input mass of carbon on your x-axis, and you have the input, the C13 of your source carbon on this axis. And so if you want to satisfy the data, you have to be somewhere on this line. Okay, so this would be an isotope excursion that would be too large. Here, your isotope excursion would be too small, so you have to be somewhere here in this range. And as I said, you have various options to do this. One option would be to put in something like 3,000 petagrams and an isotopic composition of -50, and you would get something about -3 per mil. You have other options. You can put in more carbon in the order of maybe 5,000 petagrams at -30, and you would still satisfy the isotope excursion. But the farther you go over to this side, the more carbon, CO2, you have to put into the system. Now, the CO2 dissolves in seawater, it's carbonic acid, it gets into the deep sea, and it starts dissolving carbonates. And we have constraints based on deep sea records about the extent of the dissolution during the PETM. So if you put in too much carbon, you will dissolve the entire carbonate in the deep sea, and that will be inconsistent with the records that we have. So you have to be careful if you go along this way. So, but the bottom line is you can calculate this carbon isotope excursion based on the mass and the composition of the source, and you can do this a bit more fancy. This here is my model, which actually has its own email. So if you want to play with the model, you just send an email to this email address, and I send you the model, and you can play with it, and you get also a description. So that's the end of this turbo choice segment, and the answer is 42. Okay, so one more comment about this. I explained what we did in terms of the modeling here with the carbon isotopes. And it turns out the way we do it, and if we take into account the constraints on the deep sea dissolution, we get something like -50 per mil. And this is consistent with Jerry's initial hypotheses that perhaps the carbon that went into the system and caused the excursion was perhaps methane hydrates, because methane hydrates have an isotopic composition that would be consistent with this number here. And so I want to say something about old theories. There appears to be, in the last couple of years, a number of rather strange ideas about what may have caused the isotope excursion, or what may have caused the PETM in the first place. And it's not necessary if you have a good theory. I'm not comparing Einstein with our theories, but the special relativity was published in 1905 and the general in 1916, and we don't need to replace this just because it's 100 years old. So we have to test the theory if it still holds up. And that's what we're doing. The nice thing in the model is after you calculate the deep sea dissolution and the carbon isotopes, you can also calculate atmospheric CO2 concentrations. And this here is your atmospheric CO2 in parts per million by volume. This here is the time. This here is the onset of the Paleocene Eocene thermal maximum. And if you take the numbers that we put into the model, you get an increase from about 1,000 to something like maybe 1,700 during the main event. And you can play with this initial number here. You can move it up and down. The result is very interesting because the relative increase in the total amount of CO2 in the atmosphere is relatively small. So this factor here is something like 1.6 or 1.7 is not changing dramatically if you change this value up and down. So the implication is that we have a hard time explaining the total warming during the PETM. But I'm not going to focus on this subject now. I'm going to focus on comparing it to the anthropogenic CO2 emissions. And so what you can do is essentially in a thought experiment, you can line up the onset of the PETM with the onset of the Industrial Revolution and then add the carbon and see what's going to happen. So this here is a scenario where we add 5,000 petagrams over 500 years, and the fact is that we don't know exactly how much fossil fuel reserves we have. Some estimates are in the order of 5,000 petagram. And if you do this, you get an initial spike. You could go up to 1,800 parts per million in the atmosphere within a few hundred years. That's possible. And then you get a drop. And in terms of human lifetime, this is still in incredibly long time. So this is something like 25,000 years before we will get back to even CO2 of 500 or so. But if you compare this to the PETM, that is relatively short. And so you can take my model or David Archer's model or other carbon cycle models. They will all give you a relatively similar answer for the anthropogenic scenario here. And so this is one of the big questions at the moment. Why is the duration of the PETM so long? Why does it take more than 50,000 years for the planet to stay at this elevated temperature and CO2? one answer you can give immediately is, for example, if you input the carbon during the PTM on a longer time scale. So this here is a scenario, so here's the time scale is now split up. This is over 10,000 years, and if you input the carbon over a few thousand years, it's immediately clear that you will shift the maximum PCO2 during the PTM further down because it takes longer to put in the carbon. And so this is of course our assumption about how fast the carbon went into the system. And I saw a talk yesterday, these are the exciting things about AGU, you see the latest results, where it was suggested that maybe the initial carbon went into the system over about 13 years. And we have to be careful whether this or not is possible. So if you take the same scenario I showed you before and you just put in the carbon over 13 years, you would get an isotope excursion in the surface of about 15 per mil, which we do not see if you actually have annual resolution. So I think the record is very interesting, but we need to figure out exactly what it's telling us. And of course, things are hard to imagine, but Lee Kump always tells me if it's hard to imagine, you have to imagine harder. So these questions are not settled at the moment. So, but if you go back to our PTM scenario here, this may take longer because you put in the carbon over a longer period of time, but then it just stays there. It stays there for more than 50,000 years, and then after this you get a sort of a slow drop. And this is not a model result, but we now have records of carbon isotopes, oxygen isotopes, of proxies for surface ocean acidification, and they all seem to have a very long duration. Okay, so the big puzzles for the PTM, there may be others, but it's definitely the long duration, and it's definitely the climate sensitivity. As I mentioned before, at the moment it's not exactly clear how much warming you can cause by the amount of carbon that we need to satisfy carbon isotope records and deep sea dissolution. So for the rest of the talk, I'm going to focus a little bit on climate sensitivity and whether or not there's a possibility that we can actually learn something in terms of future projections and climate sensitivity if we look into the past. And there was a paper that just came out last Friday. This is 29th of November, or last Thursday. And its title is Making Sense of Paleoclimate Sensitivity. And so the idea is, and it's really, I think, an important contribution, is to figure out that how rigorously we should look at paleo records. We have to separate timescales if we want to say something about climate sensitivity. And I want to, first of all, acknowledge a lot of these authors here. Many people have been involved in this, including myself, but they made a big contribution in terms of how we may be able to use paleo records to say something about climate sensitivity. And so one thing I've been thinking about for a while is how can we use these results that we have from the paleo records to say something about future predictions. And so one thing I want to suggest is something that I call time-dependent climate sensitivity. I'm going to explain what I mean by this. And generally, you can just write down a simple equation and say that climate sensitivity is the delta T, the temperature change, so a temperature anomaly, divided by your change in radiative forcing. But what you can also do is you can write the temperature change as something that depends on a constant, that's Planck parameter, but then it depends on the change in radiative forcing, but then also on the temperature change of temperature anomaly itself. And this is multiplied then with feedback parameters, which are fast and slow. So the point is that you're not getting only an initial temperature change from the radiative forcing, but the temperature change itself stimulates feedbacks that exacerbate the warming, and they do this on different timescales. And quite often these feedbacks are separated into fast feedbacks and into slow feedbacks. And so these fast feedbacks, for example, include water vapor, clouds, snow, sea ice, albedo, and other things. And these slow feedbacks include vegetation, non-CO2 greenhouse gases, ice sheets, and others. And as you can see from these two, it sort of seems reasonable that they act on various different timescales. And the assumption that is often made at the moment is that for the immediate future predictions, we should essentially focus on the fast feedbacks, and there's a reason to do this. But if you look into the more distant future, for example, and particularly if you want to compare this to the paleo records, at some point, some of these feedbacks will kick in. And so the point is that in the future, this climate sensitivity may not be constant, but it may be increasing over time, because most of the records that we can look at will tell you that if you wait a long time, these feedbacks get stronger and you get additional feedbacks. So what I'm suggesting is to look at a time-dependent climate sensitivity that depends on the fast feedbacks and on the slow feedbacks. And here is some parameter that if you set it to 0, you will only get the fast feedbacks, and if you set it to 1, you get all the feedbacks, including the slow ones. So if you can do this graphically, just a very simple example, if we this is the present here, and if we look into the future, say until year 3000 or year 10,000, if you would just have one climate sensitivity, you would get just a straight line. Now, if you assume that the sensitivity changes over time, and if you include fast feedbacks which will increase the warming, you would get a sensitivity that would essentially rise over time. And so this is just one possibility here. There's a large error envelope because these parameters from the past have uncertainties. So this is just giving you an example how this could look like. And if this is true or if this is correct, then we can make some simple future predictions of where the warming will go over a longer period of time if the climate sensitivity is not constant. And so this here is an emission scenario, 2,500 petagrams over 500 years. And this is an intermediate scenario. And what you want to recognize is that if we actually want to curb our emissions to about 2,500 petagrams, we would have to start reducing emissions soon, because this is already 2010. And now you can run various models, and you can ask how much warming would we get, for example, with this exact scenario. And these are sort of typical predictions that you can get, for example, for this carbon input. You may get within a few hundred years a warming of something by like 4 to 5 degrees. And then several models would predict that the warming would drop off in the next millennia or so to something like 2 to 3.5 degrees if you give it enough time of a few thousand years. Now, if you take the sensitivity that I just showed you before, which is essentially changing over time, and if some of this is correct and we would see this, then you would get a different result. First of all, your total warming would be somewhat elevated. But what is more important is that the warming is even longer. It would be prolonged. So if you take this sort of warming here, of course there are large error envelopes depending on the climate of the feedback parameters. But the important message is if your warming actually stays elevated for a long time, this is relevant to ice sheets, for example. Essentially, the disintegration of ice sheets depends primarily on the duration of the time interval of how long you can keep up high temperatures. And so I only mentioned 2 examples here. So the question is, can we actually really learn something from the past? And we can. If we look at the PETM and this climate sensitivity, then at least my count from this is that, if anything, future warming will be more likely more intense and longer than currently anticipated. And you can disagree with this, and that's fine. But I guess you would have a hard time looking into the geologic records and finding lots of examples which support the opposite. So if we look at the past climates, usually climate sensitivity seems to be elevated, even at least over longer timescales. And if we look at events like the PETM, we have a hard time explaining why these events took so long. Okay, so now I'm back at my title, and the question is, what are we going to do with this part here? Will history teach us something? So are we going to learn from our paleo records? And one interesting quote that I found from Emiliani is in the Time magazine in 1972, and he said, we may soon be confronted with either a runaway glaciation or a runaway deglaciation, both of which would generate unacceptable environmental stresses. So I'm pretty convinced that the runaway glaciation has been shown over the last 30 years is going to be extremely unlikely. If anything, we're going towards a warmer climate. And so you can ask the questions, what are going to do in terms of learning from the records from the past? And I can't answer those questions, but what I can tell you, I can give you the facts about our CO2 emissions. And the point is that our current emissions top business as usual scenarios that have been put forward about 20 years ago. So here's a graphic of emissions versus time. And the black line here, this is the IS92A scenario, which was put forward by IPCC some 20 years ago, which has been used all over the place for business as usual scenarios. And these predicted something like in the order of 8.5 gigatons carbon per year in the year 2010. Now, if you look at our actual emissions, we're topping them. There's no doubt about it. We're above 9 petagrams carbon per year at the moment. And so the question is, if you look at the recent meeting in Durban, it doesn't look like that we're going to reduce global emissions anytime soon. So I'm relatively pessimistic that we're actually going to reduce emissions. So it's going to be very interesting to look how this is going to play out in the future. And the future brings me back to Emilio Cesare. And so now Emilio Cesare returns to planet TR23A after Cyclonic decades. However, Cesare is denied permission to approach TR23A. The planet is now under the supervision of the Science Board of the Galaxy. The reason is that two new intelligent life forms are evolving in the ocean and on land. Their ancestors were distant relatives of the terrestrial species Turritopsis nuticula, the immortal, and Blatta orientalis. And here are two images of their distant relatives. And so Cesare decides to move on and study nuclear explosion and quakes on a different planet, EAR42S. And that's the end of the story, and you can read the credits, and if you have questions, I'll try to answer them.
Thank you very much, Richard. We have time for a few questions. To see if we can actually, we have to see if we actually can feel them.
We can see anyway.
Can you feel it?
Here's a question.
Oh, okay. Here, yep.
No, I haven't seen the talk. I'm sorry.
Anybody else? This is ridiculous, but it's true.
Yeah,
somebody in the back, yeah.
Yeah. Andreas. Yeah, I agree, and but I think what you can get if you do a study like you did, for example, you can get a good estimate on the upper end of the fast feedback climate sensitivity. But if you actually include the processes that are slow feedbacks, the general things that you get from the paleo records and the climate feedback parameters, the overall, if you call it Earth system sensitivity, is larger.
I would like to suggest that we defer further questions to the outside, where you can approach Richard and can actually see him, and he can see you. I would like to thank again Richard for a very unique, very entertaining, and great Emiliani lecture. And this closes the session.